The topic for today is shearing stress and bearing stress, so right after your actual stress. So let's start with shear stress. So by definition, shear stress is caused when the forces applied to an object are parallel to the object's cross-section. So these applied loads can also cause one section of a body to slide past its adjacent section. Now we have two types, your direct shear and induced shear. Direct shear is caused by forces parallel to the sectional area, hence direct, because the force itself is what's causing the stress. Now the other type is induced shear. It's caused by normal loads acting on inclined surfaces. Now you might think that that's familiar, and that's because it is. It is your shear stress on inclined plane, which is what we discussed under stress in our last meeting. So whenever we have a normal load, and then we have an inclined plane, that normal load will have parallel and perpendicular components to the incline. The perpendicular component will create normal stress, while the parallel component will create your shear stress on the incline. So the formal name of that is induced shear. Now, shear stress can also be categorized as follows: your single shear in rivet and double shear in bolt. So this is your rivet, this is a lap joint, okay, and this is your free body diagram. This is your bolt, and this is your free body diagram. And the last type is shear in metal sheet produced by punch, which is what you see here. Now, to better explain, let's have these illustrations. So once again, shear, double, punching shear. For single, we have this, your lap joint, which has a rivet. So the reason why it's called single shear is because upon analyzing, the only place where your rivet will experience shear stress is here. So it's only on one area. If we isolate the top portion of your lap joint, the top plate, okay, we have this, applied force to the left. And remember, after cut isolating, wherever you cut, there will be an internal force. Okay, so we have this internal force, which is what we call your shear force, V. And then upon using equilibrium equation, summation of forces equals 0, you'll see that V equals P in this case. And then a better look at that is the following. This is a rivet. Okay, this is where your shear stress is. Then I just separated them. So this area is the shear area. It's the area experiencing shear stress, and it's just one area. So again, that is why it is called single shear. And if you've noticed, the area for a rivet is just a circle. So later on, you'll know that when we solve for shear area, that's just pi over 4b squared or pi r squared, since again, it's a circle. Now for the second scenario, we have a bolt. Now this setup is called a clevis. So upon separating one portion of the clevis for your bolt, so again, this is your bolt, separating this section, we have this. We have an applied force downward, and then there are two sections of the bolt that were cut. So there is an internal force here and here, which we call V. Okay. And then applying equilibrium equation, summation of forces equals 0. Okay, negative P since downward plus V equals 0. You'll see that 2V equals P, hence V is just 1/2 P or P over 2, which is what we have here. So to get the relationship between your applied load and your shear force, again, you can just use equilibrium equation, which is what we've done for actual stresses again, or as well. So it's the same process. And then to get a better look, we have this. This is a clevis, and this is your bolt. Isolating that bolt, we have this, and these are the sections that experience shear stress. Those are two areas, hence this is called double shear. And then finally, we have your punch. So this your punch, usually it's a cylinder creating a hole on a sheet. Okay, so if you can imagine, what's going to happen there is this perimeter of your cylinder will create shear force hence shear stress on your sheet this way. So a better look is over here. This is your sheet. This is your punch. Okay, if you punched a hole through, this is what will be removed. And therefore, this area is your shear stress. Okay, and once again, if you can analyze, that is just simply the perimeter of your circle multiplied by the thickness of your plate. So those are your types of shear. And then let's have its equation. Remember, shear stress is tau, so tau is simply V over A. Recall that the basic equation for stress is force over area. So for shear stress, that force is just shear force, denoted by V. And then A is shear area. Now let's move on to bearing stress. Well, bearing stress is the pressure caused by surface loads between two bodies pressed against each other. So when there's two bodies in contact, if there's pressure, there is bearing stress. For example, soil pressure beneath a pier. So pier is like a column. And contact pressure between a rivet and the side of its hole. So you just heard about rivet earlier, and it's experiencing shear. So now we're also saying that aside from shear, it can also experience bearing stress, which I'll show more later on. Now, if the bearing stress is large enough, it can locally crush a material. Now, because of that, we have what we call your bearing plates. Bearing plates are used to distribute contact forces over a larger area to reduce bearing stress. So for example, here, we have this column, steel column, your bearing plate, and a concrete footing. So without the base plate, what's going to happen is the force in the column is distributed over a very narrow area. If you can imagine, it's just over here, very narrow, very small. And we know from physics, the smaller the area, the larger the pressure, which is something we don't want in designing structures because it could easily lead to failure, especially for concrete footing, because concrete, although it is strong against compression, it's weak against shearing, and this narrow area can create shearing in the concrete footing. So the base plate is there to distribute the load from this column to a larger area on the footing, hence minimizing stress. Okay, now let's go back to that rivet. Okay, so it was mentioned that rivet also experience bearing stress. So to illustrate, we have the following drawings. So again, on A, we have a rivet and a lap joint. Now in actual, okay, what happens is, let's take this top part of the rivet or of the lap joint. It's pulling towards the left. So what's going to happen is the right side of your joint or lap joint or plate will push against the right side of your rivet. And then, again, because this is pulling, there could be a gap on the left side. Okay, so since there's a gap, there won't be any pressure, hence no bearing stress. And then since there is contact here on the right, that is where your maximum bearing stress is. So in actual, bearing stress in a rivet is not constant. But even though that is the case, it is common practice to assume otherwise. So we're going to assume that the bearing stress is uniformly distributed, not on the rivet, but on a projected area as seen in figure C. Okay, so to better understand that, let's have this figure. So once again, this is your plate. If your force is directed to the left, this side will push against your rivet. So this is the actual contact area, the actual area experiencing bearing stress. There's no stress here since they aren't in contact. Now, instead of analyzing it that way, we're in stress is force over area, area being a curved area, we'll use a projected area instead. And by projected area, I mean this. So this is your rivet, projecting it on a flat surface. Okay, so any flat surface. And for example, on the side of your plate, you'll see that you'll get a rectangle. And then the base of that rectangle is the same as the diameter of your rivet. And the height of that rectangle is the same as the height of your plate. So this projected area is simply dP. Okay. So In conclusion, the equation for bearing stress is sigma sub b for bearing equals PB over AB, where PB is bearing force, A sub B is projected area, and we already know bearing force, or rather projected area, is just BP. Okay, and then you'll be able to solve for PB using equilibrium equations and the free body diagram. So that's it for the concept. Now let's move on to examples. So example number 1, so please ready your calculator for faster solving. The lap joint shown in the figure is fastened by 4 rivets of 3/4 inch diameter. Find the max load P that can be applied if the working stresses are 14 ksi for shear in the rivet and 18 ksi for bearing in the plate. Assume that the applied load is distributed evenly among the 4 rivets and neglect friction between the plates. Okay, so let's analyze. We have a lap joint, we have 4 rivets. What we're looking for is the maximum load P given our stresses. Okay, so we're looking for P. Now the first step is to write the given. We're given diameter of rivets, so I'll call that D sub R, which is 7/8 or rather 3/4 inches. And then working stress, shear 14, bearing 18. So let's write that as well. So shear symbolized by tau, 14 ksi, bearing sigma sub b, 18 ksi. Now ksi, for those who don't know, is simply 1000 psi. Okay, so that is what that means. Now let's try to analyze it this way. Remember, when we were solving for actual stresses, the amount of working stresses we had is equal to the amount of equations that we need to use. We have 2 equations here, or rather 2 working stresses. So we're gonna analyze in 2 ways. One for shear, one for bearing. So let's start with shear. Shear happens in the rivet. Okay, so rivet. Okay, so what's happening there? Rivet experienced shear. So let's draw a free body diagram first. Okay, this is your applied force, and your shear or your rivets will counter that or react to that. So that means there will be resulting reaction forces over here. Okay, and then let's call that V, because those are your shear forces. If we try to isolate this top portion, you'll see that the cut part is a shear reaction or shear force. And then upon doing that, you can do equilibrium equation. Summation of forces equals 0. Let's say this is negative direction. So negative P. And these are all positive directions. So plus 1, 2, 3, 4, 4V equals 0. From this, we can conclude V equals P over 4. Now, you can only do this because we have this definition, distributed evenly. Okay. So that's why all of them are just V reactions, the same reaction, because it's distributed uniformly. If it's not, you can't do what we just did earlier. Okay. So you can solve it this way, or you can just use logic. Since P is distributed uniformly upon the rivets, therefore all the rivets are just carrying a fourth of that force. Hence, shear force is just P over 4. You can do that as well. Just immediately write P over 4. That's fine. Or you can go through the equilibrium equation. Okay, now I have shear force. Next step is to use your working stresses. So shear, we're going to use shear stress. So tau equals V over A. We already know V is P over 4. And A, shear area of a rivet. We mentioned that earlier. Shear area of a rivet is simply the area of a circle. What's the area of a circle again? Anyone? What's the area of a circle? Correct, John and Jan. Rico Briones. It's pi over 4 d squared or pi r squared. What we have is diameter though, so I'm going to use pi over 4 d squared. Okay, and then let's sub 14 KSI. Again, that's just 1,000 pounds equals P, which is what we're looking for, over 4, over pi over 4, and D. D's shear area, again, that's for the rivet. Diameter of rivet is given, so 3/4. From this, you can solve for P. Please solve. What's the answer? Correct. Christian and Mariah. Danaga. Cavero. It's 24.74. Now let's figure out the unit. Okay. This is in KSI. 1,000 pounds per square inch. This is in inch. So the resulting unit is 1,000 pounds. Now we have a symbol for that, or a unit for 1,000 pounds, and that is kips. Okay. So if we're using KSI, the resulting unit for force is kips. Now that's not our answer yet. That's just a possible answer. So let's just put that aside. Now let's move on to analyzing the plate, which experiences bearing stress. Okay, so let's draw another free body diagram. As such. So this is your plate. I'm gonna isolate the top part. And then let's say this is the projected area. Okay. And then I'm just gonna draw one bolt, okay? Just to simplify what we're doing. And then let's say there's a bolt here. So this is the projected area. And then there's an applied force P right here. That's your P. And then if you cut it here, you'll see that this is the shear area here at the bottom. And we're talking about bearing. You'll see that the resisting portion is on this side, but again, we're using projected area. And then the reaction force there would be this way. Okay, that's your PB. And then again, using equilibrium equation, summation of forces equals 0, negative P plus PB equals 0, so PB. So that's not just one. Remember, there's 4 of those. So I'm not gonna draw 4 rivets anymore. I'll just multiply this by 4. Okay, to denote that there's 4 reaction forces for bearing. So for PB. So therefore, PB is just 1/4 P. Okay? And from that, we can use equation for bearing stress. So PB over projected area. Again, PB, 1/4 P. What's the equation for projected area again? This is the projected area. So what's the equation? Correct burst. Manual. It's dt because this rectangle has the same base as the diameter of this bolt. Okay, so this also d, and then this height is the same as the thickness of your plate. So this is just dt. And now let's sub in our values. 18 equals 1/4 P, or P over 4 all over. Diameter again is 3/4. And then thickness given 7/8. From this, please solve what's P. Correct, John and Tristan. De los Reyes Guico. Okay. 47.25, and once again, unit kips. Again, that's just a possible answer. The question is, what's the maximum allowable force P? So everyone, please answer. What's P max? Is it 24 or 47? Again, answer in the chat, 24 or 47. Okay, very good. Almost everyone got it correct. The answer is 24. Very good. Now remember, again, to reiterate, when we're looking for maximum force, you're going to choose the minimum value because otherwise, one of them will fail. And that's it for number 1. Do you have any questions? Please answer in the chat. There's a question, paano nakuha yung 24.74? Do you mean this or this? Huh? Okay, so we got this because when choosing maximum force, as mentioned in the previous lecture, you should use the smaller value. 24 is less than 47. Now, the reason is if you choose the other one, okay, therefore the rivet will fail because the rivet can only handle this much force, okay? So anything more than this, your rivet will fail, which is not what we want. So I can't use this because again, rivet will fail. So the answer is this, okay? And then how do we get this? Using this equation. So we got the shear force in each rivet using equilibrium equation. So V equals P over 4. Shear stress is shear force over area. So we already know that shear force is P over 4. Area is a circle because the shear area of a rivet is a circle as seen here. Okay. So pi over 4d squared. So now we just sub in everything. 14 KSI, P is what we're looking for, over pi over 4. 74. Yeah, thank you for the correction. Okay, na, gets na. All right. Next. Number 2. The lap joint shown in the figure. Not that. What force is required to punch a 20 millimeter diameter hole in a plate that is 25 millimeters thick? The shear strength is 350 meganewton per meter squared. Once again, let's write the given. We have diameter of a hole, so I'll call that BH, 20 millimeter. And then we have the thickness of the plate, 25 millimeter, and then shear strength, 350 meganewton per meter squared. So let me write all that. Thickness, 25 mm, and then shear stress limited to 350 meganewton per meter squared. And remember, that's the same as MPa. Okay, so keep that in mind. Now what's happening here is we're looking for the force in order to punch a hole with this dimension on a plate that has this shear strength. Okay, so we're going to base our equations on this shear strength. So let's draw what's happening. So you have a hole. Okay. Let's say this is your punch, your cylinder, right? Okay. And then it's going to produce a hole like this. And then that hole will be on this plate. There. With this thickness T. Therefore, this is the hole that we want. Okay. So that is what's happening. Now the question is, what force is needed? Okay. There. Now upon analyzing this, if this is your shear force, remember whichever object is being cut, that is where your internal loads will appear. Okay, so your plate is being cut this way, so that is where your reaction will be. And the reaction is opposing that applied force. Therefore, reaction is this way. And then there's only one area resisting that force, so that's just one, so that's just V. Therefore, we can say V equals F using summation of forces equals 0. Okay, now that we've established that, we've figured out what V is, you can use your working stresses. So shear equals V over A. Again, V is just your F, your applied force. And then A is the cross section. A is the shear area. Can anybody tell me what's the equation for this shear area for a hole? Close. Pi d is just the perimeter. What is this? Correct. Cyrus and Jan. Vico and Tenorio. Very good. It's pi dp. Because again, pi d, perimeter of your circle, but I need the thickness because this is the actual area that's being cut. Okay? So pi dp. There. And now let's sub 350. Again, that's the same as MPa. Force is what we're looking for over pi times d, diameter of your hole, right? Diameter of this, which is given 20 times thickness d, thickness also given 25. From this, please solve what's F. Correct, Ralph and Chloe. When seal McCrohan. So it's 549,778.71 unit. This is MPa, Newton per millimeter. 20 and 25 are both in millimeter. So there's consistent units. The resulting unit for force is Newton. Now that's a large number. So maybe the question would ask, what's the force in kilonewton? Now, if the question asks that, you can just convert this by dividing by 1,000. Your final answer would be 549.78 kilonewton. Okay? In our problem, however, nothing was given or no unit was specified. So answer could be either. So that's number 2. Now let's have number 3. Number 3, as shown in the figure, a hole is to be punched out of a plate having a shearing strength of 40 ksi. The compressive stress in the punch is limited to 50 ksi. Letter A, compute the maximum thickness of plate in which a hole 2.5 inches in diameter can be punched. And letter B, if the plate is 0.25 inch thick, determine the diameter of the smallest hole that can be punched. Once again, let's analyze. We have this punch, a cylinder, and we need that to punch a hole on this sheet. And the question is just asking for part A, what should be the diameter, or what should be the thickness, and then for part B, what should be the diameter. given your working stresses. Okay? So now let's write the given. Shearing strength in plate is 40 KSI. Strength. Now don't get confused. Strength and stress are the same in terms of solving. Okay, so strength just means it's the maximum stress your object can handle. So let's just write it as stress. So shear stress equals 40 KSI. And then we also had your bearing stress, compressive stress rather, 30 KSI. So that's it for the given. Let's start with part A. 50. Compute the maximum thickness of plate in which a hole 2.5 inches in diameter can be punched. So we're looking for thickness given diameter of hole 2.5. So I'll write that as well. DH 2.5 inches. Again, this is 50. Okay. So to solve for thickness, figure out what equation has thickness. That is shear stress, right? Shear stress equals V over A, and we already know that A is simply pi dt. Okay. I have stress. Okay, good. V, I do not have V. Even if I draw a free body diagram here, I'll just conclude V equals P. Okay, so that's also an unknown. So I got two unknowns here in this. So I can't use shear stress yet. So that means I should use the other one, which is compressive stress. So this is the compressive stress in punch. And we know compressive stress is just simply P over A. P being the applied force creating the compression. So let's do that. 50 got P over A. So recall your actual stress equation, P over A. A is the cross section of your object. Our object is the cylinder. So can anybody give me what is the area of that in terms of compressive stress? What's the equation for area? Okay. Remember, if we have a tube, we have this P, normal force P, stress is P over A. What is A? Correct, Jan. Pi over 4D squared. Because again, over 4. And also Joffrey, correct. I call for normal force, for normal stress, area is the cross section of the object itself, perpendicular to the applied force. So this is the perpendicular area, which is a circle. So pi over 4D squared. So pi over 4 D, diameter. This is diameter of hole. But remember, the diameter of your punch should be the same as the diameter of the hole in order to get the same dimension. So I'm going to use DH as well. So that's also the diameter of your punch. So 2.5 squared. And then from this, please solve what's P. Correct. Mariah and John. Benedict Cavero family. It's 245.44. Okay, that's just P. So store that in your calculator because we're going to use it later. And now, since I know P, I can finally use the shear stress, V over A. You already know V is just P. P over shear force, shear area A. And again, since it's the same scenario as number 2, we know A is pi dt. 40 equals P, which is this, over area, pi, diameter of hole, 2.5, thickness, P. Oh, don't forget to check if your units are consistent. KSI, this resulting P is in kips, right? Because this is also KSI and then inch. So this is in kips, KSI, inch. So they're all consistent units. So no need to convert anything. And then from this, please solve what's P. Correct. Anne and Benedict. De Guzman. It is 0.78 inches. Okay, great. That's part A. Now let's move on to part B. If the plate is 0.25 inch thick, determine the diameter of the smallest hole that can be punched. So now we're looking for diameter given thickness. Thickness, 0.25 inch. We're looking for D. Now upon analysis, you'll see that both compressive and shear stress needs the diameter. Okay? So that means no matter where you start, there's no immediate answer. Okay, you'll just get an equation at the end. So that means you can just start wherever you want. Because no matter where you start, you have two unknowns. Okay, so it's your choice. Let's try starting with compressive stress again. So this is P over A, which is just P over pi over 4D squared. And that is 50 KSI equals P, again, we don't know P, over pi over 4D squared. I don't know P, I don't know D squared, there's nothing to solve for there. However, I will rewrite this equation to make it easier to substitute. So I'll write this as P equals, so 50 times pi over 4, I think that's 12 pi over 12.5 pi D squared. Okay. And you can just call that equation 1. Afterwards, you can move on to the next equation, V over A, which is again just P over pi dt. This is 40 equals P, and P is this, okay? Sub 1. So it will become 12.5 pi d squared over pi, the thickness given, 0.25. And as you can see, we can cancel a few things. I can cancel pi, I can cancel the d in the denominator. And then from this, you can solve what's d. Correct, Anne and Ralph. Buensil de Guzman. .08 or 0.80 if you want 2 decimals, and then this is inch. And that's it for numbers 2 and 3. Do you have any questions? Please answer in the chat. Ma'am, paano po nakuha yung 0.78? P is 245.44. So 40 times pi times 2.5. And then divide 245.44 by what you got. You'll get 0.78. P is what we're looking for. Okay. All right. Ma'am, bakit magkaiba yung formula ng area for two equations? Because the area affected is different. For compressive stress, again, this is your actual stress. The area is the area perpendicular to your applied force. This is your applied force, so perpendicular area is this, which is the area of a circle, so pi over 4d squared. For shear stress, this is shear stress, we have shear area, which is the area parallel to your force. This is your force, so area parallel to that is this. And if you look at the 3D, it's going to look like this. Okay, so that's the same here. As you can see, that's perimeter times thickness of your plate, right? That's the parallel area. Okay, so pi dp. So that's why it's different, because the affected areas are different. For compression, it's the perpendicular area. For shear, it's the parallel area on the plate. Okay? All right, any other questions? No more? Okay. Great. No questions, let's have the next one. Number 4. Okay, so for number 4, find the smallest diameter bolt that can be used in the clevis shown in the figure if P equals 400 and the shearing strength in the bolt is 300 MPa. Okay, we're given shearing strength, we're given applied force, we're looking for possible diameter of the bolt. Okay, let's write all of that. Once again, applied force P is 400 kilonewton. And then shearing strength of the bolt is 300 MPa. We want to know what should be the diameter of our bolt to resist that force. Okay, to solve for that, we cut isolate. Okay, I'm gonna cut this portion of your bolt instead of this. Okay, so cutting that, we have something like this. So this is your applied force P. Okay, and then your bolt is cut over here. Like that. Okay, so there. And again, wherever you cut, that is where internal loads will be. There's a cut here, so there's an internal load here, and then another internal load. And by now, you should have understood that that internal load is the shear force. So V. Therefore, summation of forces equals 0, negative 2V plus plus P equals 0. V is just P over 2. Okay, now you have, and P is 400. Now you have equation for V. Next, you're going to use the working stress. Our working stress, again, is shear stress. So shear stress equals V over A. Once again, V is this. So P over 2 over A. Our A is the parallel area of your bolt. And we already know a bolt has cross-section of a circle. So this is pi over 4d squared, area of a circle, as you can see here. That's the shear area. So pi over 4d squared. And V, diameter of your bolt, is what we're looking for. So now let's sub in our values. This is 300 MPa equals P. P is 400 kilonewton. This is MPa, Newton per millimeter squared. So I have to convert that. So 400 convert to Newton. That's just times 1,000 or times 10 raised to 3. Okay, again, this is just converting kilonewton to Newton. Then over 2, all over pi over 4 d squared. From this, you can solve for d. Please solve. What's the answer? Correct, Stephen? And Janelle, Espanol, Jorge. 29.13, and then unit, once again, Newton millimeter, so our resulting unit is millimeter. So that's it for number 4. Any questions for number 4? Please answer in the chat. Okay, no questions. Great, let's have number 5. So 5 is a bit more complicated, as you can see. A 200 millimeter diameter pulley is prevented from rotating relative to 60 millimeter diameter shaft by a 70 millimeter long key as shown in the figure. If torque is 2.2 kilonewton meter applied to the shaft, determine the width D if the allowable shearing stress in the key is 60 MPa. Okay, so to explain what's happening, you have this pulley, right? This pulley should rotate. Rotation would be due to the torque applied on this shaft. However, it's prevented from rotating because of this white key over here. Okay, and this key has the following dimensions. It's 70 millimeters long, 10 millimeters height, and we're looking for this thickness B. Okay. So now, in order to get that thickness B, we should know what kind of stress it's going through. Now, to know what stress, it's already given in the problem. We're given shearing stress. So we'll base it off of that. Okay, so this key is apparently undergoing shearing stress. So now, I have shearing stress. We're looking for area. What I need is shearing force as well. So first, let's figure out what's the shearing force on the key. Okay, so let's write out the given. Torque 2.2, shear stress 60. Okay. So torque 2.2 kilonewton meter. And then maximum shear stress is simply 60. Okay. So again, our first thing is, what is that shear force on our key? Okay. So to figure that out, you can imagine what's happening. Okay. This is your shaft. If it wants to rotate, okay, it's gonna push through this key. And again, we know that that's shearing stress. But specifically where? Remember, shearing stress happens when force is parallel to the area. This is gonna rotate. So there's gonna be a force in the direction of rotation. Specifically here, it's gonna be this way, right? This way. Okay. And then the parallel area to that force would be this, the portion here. And this rotational, this force is due to the torque of your shaft. Okay. And remember, torque has the equation RF. And so F is what we're gonna get. Okay, so once again, we know that that shear force is gonna be due to the rotation of this shaft, and it's gonna be applied over this area. So to figure out what that force is, let me just draw a 2D representation of our shaft and the key. That's your shaft. This is the key. Okay. And then once again, the shear stress is along the surface of your shaft here. That is where shearing happens. And it's due to this applied torque T. Now remember, for torque is force times distance. Distance to wherever your object is rotating on. This cylinder or this shaft is rotating about its center. So this is the rotational axis. And then we know that that force, the force that we need is the one here. Okay? This F. So this is your R. Because again, R is moment arm from axis of rotation to applied force F, and this is your F. From that drawing, we can conclude torque equals RF. Torque is given 2.2 kilonewton meter. 2.2 kilonewton meter. And then R, again, distance from center of rotation or axis of rotation to applied force, which is this, which is just the radius of your shaft. The diameter of your shaft is 60, so that's just divided by 2, so it's 30 millimeters. This is kilonewton meter, so I have to convert that to millimeter. Meter to millimeter is just times 10 raised to 3. Equals 30. Again, radius of this shaft. And then once again, F is what we're looking for. So from this, please solve what's F. Correct, Anne and Chloe. Macrohon de Guzman. Ito ko na eh. Ba naman? Correct, Marces Santiago. 73.33. And then unit, I'm gonna write it so that we don't forget. This is kilonewton meter. So kilonewton. Okay, now I have F. Next, let's analyze how that F is affecting our key. Okay, so I'm gonna draw the key. Let's say it's like this, right? And then depending your cylinder is something or shaft is somewhere there. So this at this point, okay, and that is the surface of your shaft. Okay. Therefore, the portion being sheared is this. Okay, so this is your shear area. Because again, along that is where your shaft is. Okay. And then there. Okay. Okay. So basically, this F is this way, right? Tangent to your shaft. And then to resist that, you have this reaction force, which is your shear force, B. And then we can now use our shear stress equation, V over A. We already know V is just F, right? So therefore, V is equal to F. So this is F over shear area, which is this shaded region. Now to get that shear area, this is just the base of your key, right? That's B. And this is just the length of your key. And that length is also given. It's 70. So 70. Therefore, this shear area is a rectangle. So that's just base times height or length times width. Length is 70 with this B, so this is 70B. And now let's plug in our value. 60 MPa equals force. Our force is in kilonewton. Our stress is in Newton. So let's convert that again. So 73.33 kilonewton times 10 raised to 3 to convert it to Newton all over 70B. B is what we're looking for. Please solve what's B. Correct. Marces, Santiago, and Steven Horka. Marces. 73. Okay. Is it? Oh. 17.46. Oh, sorry, not Horka. My bad. Wait, tama. 17.46 millimeter. That's our answer. So that's the minimum required thickness of your key to prevent motion of your shaft. Okay, so that's number 5. Any questions, please answer in the chat. Okay, no questions. Great, let's move on to number 6. Okay, number 6. The members of the structure in the figure weigh 200 pounds per foot. Determine the smallest diameter pin that can be used at A if the shearing stress is limited to 5,000 psi, and then assume single shear. So we have this figure. Weight, distributed weight is given because there's a per feet in the unit. The question is, what should be the diameter of pin at A? Okay, so let's write the given first. We have, again, distributed weight. So I'll call that W. And then we also have maximum shear stress limited to 5,000 psi. And then single shear. Okay. So to do this, again, the question is what should be the diameter of pin at A given this condition? Okay, so that's our condition, shear stress limited to 5,000. So this shear stress, meaning what I need is shear force, the shear force being experienced by A. And shear force, again, is the area or force parallel to your object. The object in question here is your pin. Okay, so if we try to draw this support, this is your pin, okay, something like that. And the force parallel to this pin, the cross-sectional area of the pin, is just the reaction R, right? This force parallel to the area of your pin. So I gotta get reaction. So that's it. Get reaction. So let me draw that out. Reaction at A. Since this is a pin, there's a vertical and horizontal reaction. So I'll call it AY. I'm going to assume that's upward. And then for the horizontal, I'm going to assume that's to the right. I'll call this AX. Okay? Now, remember I mentioned before, to get reaction at one support, you get moment on the other support. Now, if you do that here, moment at C, you'll see that AX has a moment about C and AY has a moment about C. That's two unknowns, meaning I can directly solve for a reaction using that method. So, the only way to use moment about another support to get reaction is when these supports lie on the same horizontal line. So let's say if this C was over here, right? And we did summation of moment at C, AX would cancel out because that passes through C. So we can solve for AY. Okay? However, that's not the case, so we can't do that. Instead, what we can do is using method of members. Now you might ask, why not method of joints? Why not method of sections? Well, because of the presence of this. There's weight there, so therefore it's not negligible. We have to include that in our computation. And remember, for method of joints and truss, method of joints and section, weight is negligible. So that means this is a frame, so I should use method of members. So the first step in method of members is isolating a member. I need A, so I'm going to isolate AB first. Okay. There. That's your bar, right? And then I got reactions here already, so I'll just apply that to the drawing. This is AY, and then this is AX. And don't forget, we have weight. Remember, for a homogeneous material, weight is simply at the centroid. For this, it's simply at midspan, so somewhere here. Let's call that W1. And then there's going to be reactions at V as well, because that's also pin connected. Anywhere there's a pin, there will be reactions. So you can just guess the reactions here as well, similar to your joints and sections. I'm going to guess maybe BX is to the left. Maybe BY is downward. Again, this is just randomly guessing. Okay? So now, next step, I need to know what the value of this is. It's not 200, because that's pound per foot. That's not a point load, that's a distributed load. So to convert this to a point load, I have to multiply it by its length. So I have to get the length of this. Let's call that L1. Okay? Now to get L1, if you've noticed, if I do this, I have a right triangle with base 4, and then with height, this, which is 6 minus 2. Okay? So I'll apply that in our free body diagram. Again, base 4, height, 6 minus 2, which is also 4. From that, we can solve for L1. Square root of 4 squared plus 4 squared. And then just to minimize the amount of numbers we're storing, I'll just write out its simplified form instead of its decimal. So that's 4 squared of 2. Okay, so I'll use that instead of the decimal form of that. And then from this, we can finally solve for weight, W1, which is again, to convert distributed to point load, because this is a distributed load, just multiply it by the length. So that's 200 times L1. So please solve what's 200 times 4 square root of 2. Correct, Joffrey and Eric Ablao Cofreros. Let's see. Good. It's 1131.37. And then please store this in your calculator because we're going to use it in the future. Now, afterwards, I can finally use your equilibrium equation. Okay. So again, we have three choices, fx, fy, moment. If I do fx, there's two unknowns, ay, by. If I do fx, I got two unknowns again, ax, bx. So there's nothing to solve. Even if I do moment at A, there's two unknowns. Moment at B, there's two unknowns. So what should I do? So you should approach it in a way that it's easy to solve one of the unknowns, okay? And usually, you're solving for a joint that has two members attached to it, because that means you can create two equations from it. Two equations, two unknowns, you can solve. And that joint is joint B. AB attached to it, BC attached to it, you can get two sets of equation to figure out BX, BY. Okay? Now, knowing that, that means I have to start with summation of moment at A to get the two equations for BX, BY. Okay? The summation of moment A at 0. AY, AX passes through A, so ignoring that. Let's start with W1, rotate about A, that's clockwise. Right? Clockwise. So positive W1. And now the question is, what is that perpendicular distance? What is this length? Now, since this is weight acting at the centroid, the actual span and the horizontal and the vertical components are all just divided by 2. So if this is 4, distance from center to edge, or distance from weight to the edge, is also half of that. So that's 2. And so if this is 5, then this is 2.5, okay? Again, that only applies for weight. So therefore, perpendicular distance 2. Next, bx. Rotate bx about A, that's counterclockwise, negative bx. Perpendicular distance is this, which is 4. So times 4. Next, by. Rotate, that's clockwise, so positive by. Perpendicular distance is this, which is 4. There's no other force, so equate to 0. W1, I know, it's this. Bx, by, I don't know. So there's two unknowns there. Nothing to solve, so I'll just call this equation number 1. Okay? Now, the other equations we can use is, again, summation of forces x and y. However, if you try that here, let's start with summation of forces x. Right? Ax to the right, bx to the left equals 0. I can't solve for anything because I gotta know bx first. Okay? So, we'll just put this to the side for now and move on to the next member, which is member BC. Okay, let's draw again. Kind of like that, right? And then apply your forces. There's another weight here. So this is I'll call it W2. Let's change the drawing though. So roughly at the center, W2. And now, here's the thing about method of members. What you assumed on the direction on a connecting member should be the opposite on the other connected member. So that means A, B, and BC are connected at B. So they both have BX, BY. Assume the opposite on the other one. So for example, if this is to the left, BX to the left, then you should draw BX to the right. Similarly, if this is downward, you should draw BY upward. BY. Okay? So it's not compression tension for method of members. Okay, it's left, right, up, down. Okay, so that's it. And then I won't even draw reaction at C because we already know I need equations for Bx, By to get this. So I'm gonna do moment at C. And you don't need the reactions of moment at C. Okay, now that that's established, there's a weight here. So that means I need to figure out what that value is. And to do that, I need to get the length first. So let's call this L2, length 2. And it's this right triangle, base 3, height 6. So to get L2, that's just square root of 6 squared plus 3 squared. Once again, I'll give you the simplified form instead of the decimal form, and that is 3 squared to 5. There. And then W2 is simply 200 L2. Please solve what's W2. Correct? Christine, Franco, and Christian, Denaga. Okay. It's 1341. And once again, store that in your calculator. And then you can use summation of moment at C equals 0. And this is C. Okay. So let's start Bx, rotate about C, that's clockwise, therefore positive Bx times perpendicular distance to C, that's 6. Next, By, rotate about C, that's also clockwise. So plus By, perpendicular distance, 3. What else? W2, rotate about C, that's counterclockwise, so negative W2. And then get perpendicular distance. So similar to what we had in AB, this is the perpendicular distance, right? Which is just half of this. So that's 1.5. So times 1.5 equals 0. Once again, 2 unknowns. So there's nothing to solve for yet. But now we have 2 equations, 2 unknowns. You can solve for Bx and By using 1 and 2. Okay? So therefore, please do simultaneous equations. What's Bx? So for those who want to use their calculator, again for Casio FX991ES, that is mode equation. To me, that's 5. And then choose A and X plus B and Y equals Cn, because that is 2 unknowns, which is what we have, 2 unknowns. And then when you press that, you'll get this matrix, 1, 2, A, B, C. Okay, 1 and 2 are the equations. So let's start at 1. A is the coefficient of your first unknown. So let's say my first unknown is Bx. So the coefficient of that is negative 4. And then for B, that's the coefficient of the second unknown. So that's By. So that's 4. C is the constant transposed to the other side. So W1 times 2 transposed to the right, that will become negative 2 W1. Okay, and then just do the same thing here. And then press enter, you'll get the answer. So please solve what's Bx. Correct, Christine. Franco. Okay, who else? Give me 100. I'll do the same thing here. So that is Bx, right, is my first unknown. So there should be 6. By is 3. And then convert to the right. That's positive 1.5 W2. Press enter. The first number will be your Bx. And then press enter again. You'll get By. Or you can solve manually. So please do that and solve. Okay, very good. Cyrus, correct. Tenorio. It's 412.17 And then what's by? Correct. Tristan and Ubaldo. De los Reyes Ubaldo. Negative 153.52. Okay, so that negative sign just means my assumption for direction is incorrect. So instead of downward here, it's upward at AB, and then instead of upward, it's downward at BC. But that's fine. I don't need that. I need this. Now that I have BX, I can finally solve for AX. So AX is just 412.17. Okay? And then we can do summation of forces Y. Right? So AY, since upward positive, downward negative W1, downward negative BY. So since I didn't correct my direction here, it's still downward. So that's still downward negative equals 0. And then from this, you can solve for AY, but please take note, BY is negative. So include that negative sign here, okay, because I didn't correct the direction. So please solve what's AY. Considering W1 is 1131, BY is negative 153. So what's AY? Correct, Christine? Who else? And burst. 977.85. Okay. Now you might wonder, what will I do with that? I have AX, AY. Now what? Remember, from the start, the goal here is to get the reaction at A. These are just the components of the reactions at A. I need the resultant. And remember, if we have components, to get the resultant reaction, that's just square root of AX squared plus AY squared. Okay, please solve. What is that? What's RA? Correct, Christine. And Ralph. Gwensil Franco. $1061.17. Okay, correct. Now that I have RA, I can use my stress. So stress equals V over A. And remember, okay, that reaction is equal in magnitude to the shear force. So this is RA. And once again, this is a pin. So cross-sectional area of a pin, the area that's parallel to this reaction is just a circle. So pi over 4b squared. This is 5,000 psi. RA is in pounds, right? Because our weight was in pounds. So no need to convert. So RA is what we had here. So store that. Over pi over 4d squared. And then from this, you can solve for d. Please solve. What's the final answer? Correct, Ralph. And Gwyneth de Guzman Bonsil. .52. Again, this is in PSI, pounds per square inch. So unit is inch. And that's it for number 6. Do you have any questions for number 6? Please answer in the chat. Okay, no questions, great. Since we're almost out of time, I'll end the problem solving there. On Tuesday, we'll continue number 7 and number 8. I've uploaded this lecture in Blackboard already. And then on Saturday, we have your seat work number 1 available the whole day. Soft deadline 11:59 p.m. on Saturday as well. There won't be any Zoom meeting, so you can answer the seat work whenever. Just keep in mind the deadline. Hard deadline is after a week. And then again on Tuesday is just continuation of lecture and starting a new lecture as well. And then a few reminders for those who haven't answered the diagnostic exam, please do so. We have until Saturday. Don't have to message me, just answer it. And for those who haven't yet, please watch the orientation videos and PDF file. Oh, I have a question. Ma'am, aside from solving problems repeatedly, ano po pa ang pwedeng gawin para mas gumaling mag-analyze? Oh. Well, what helped me really understand mechanics is not just repeatedly solving a problem. Although it helps you build good habits in solving. It helps you become organized. But aside from that, try to solve problems in a different way. So for example, here, I've solved it this way. You can try solving by starting with summation of moment at B first and create an equation for AX, AY. And then try doing other equilibrium equations. Okay? Because in mechanics, a problem can be solved in multiple ways. Right? So I've mentioned before in other problems that like, I isolated the left, you can try isolating the right. And if you got the same answer, then that means you understood the problem. Because you're not following the method I chose, you're following your own method. Okay? And that's important. You don't have to copy how I solve. What's important is for you to figure out what makes sense for you. And to do that, you have to practice solving in a way that's different from your professor. Okay. But again, you should do that only for applicable problems. Like again, if I isolated the left, you should isolate the right and try to solve it in a way that makes sense to you. If you got the same answer, then great. If not, figure out where you went wrong. Okay, so that's one of my tips. Okay. Understand the concept and then try to figure out how you solve a problem. Don't just copy the way your professor solves. Because that means you understood the concept. And when you understand the concept, you can answer other problems that were not given by your professor. Okay? Now, any other questions, concerns, clarifications? None? Okay. So once again, to reiterate, it's important to understand the concepts, okay? Not just memorize how to solve a certain problem. And with that, since you don't have any more questions, I'll see you on Tuesday. You may go. Goodbye, class.
Thank you po.